Okay, so let's have a look at this lab here. So we're going to do a little bit of key exchange, some public key, symmetric key, and also some hashing. So we generally go through using the Diffie-Hellman method, implement some symmetric key methods, then go on to public key encryption, and then how we store the keys and how we create digital certificates, and then we'll finally look at hashing methods. Okay, so what I'm going to do is I'm going to use Kali for this, and I'm going to select my public facing Kali machine here. Okay, so if I just expand that, it's going to be easier to be able to see what we're doing. Okay, so the first part, we're just going to implement some Diffie-Hellman from there. So just let me move that, and then I'll move that over here. And this is our Kali prompt. Okay, we'll just have a quick look to see what our IP address is. And you can see in this case, that's my IP address there. So the first thing I'm going to do is to open up the calculator, and we'll do some Diffie-Hellman calculations. Okay, so let's say we have a G value of 2879 and a public modulus of 9292. So just let me take a quick copy of that. So G is 2879 and N is 9929. Okay, Bob, we'll call it B, selects 6, and Alice, we'll call A, selects 9. Okay, so let's do the calculation. So the value that that Bob will send Alice will be the G value, which is 2879 to the power of 6, and then mod 9929. Okay, so that's so Bob, we'll call it big B here, 4850, and now we'll calculate what Alice will send. So Alice will send G, which is 2879 to the power of 9 mod 9929. So Alice will send 3614. Alright, so the key that we generate will be Bob's value, which Alice will receive, to the power of the A value mod N. So let's see what we get that as. So Bob's value is 4850 to the power of Alice's value 9 mod 9929. Okay, so that comes out as 4868. And now we'll see if Bob gets the same key. So it's Alice's value to the power of B mod N. So Alice's value is 3614 to the power of Bob's value 6 mod N is 9929. And that's 4868, which is the same as we have for Alice. Okay, so that's proven that that actually works. Okay, so try it yourself in the lab. if you prefer to use Python, then with Python, we just can take G equals 2879, n is equal to 9929, x is equal to 6, and y is equal to 9. The value that, so we'll make that Bob is 6 and Alice is 9. So the value that Bob sends is g to the power of x mod n, and the value that Alice sends is g to the power of y mod n, e to the power of a mod n. Just go back over this one again. So that's b. Okay, we'll print a and we'll print b. That's fine, that's what we got before. So the key 1 is equal to a to the power of b. So this is the value that Bob will generate, and the value that Alice will generate, she receives b to the power of a mod n, and we'll just print k1 and we'll print k2, and they should be the same. Okay, so that proves the Diffie-Hellman method works. Okay, so now we'll go through the commands that we have. So the first we'll use OpenSSL and implement our symmetric key encryption. Okay, let's see if our paste works, and it does. Okay, so here are all the methods we can use for symmetric key, such as blowfish, ARIA, DES, AES, and so on. We want to have a look at the version that we've got, and we can just type in our command, and we can see we've got version 1.1.1 n. If we want to see if we have a hex number, we can easily perform this command. Sometimes the hyphen comes out a little bit strange, so make sure you replace it with a proper dash. So the first thing we'll do is we'll encrypt with AES encryption, CBC. Just to make sure all our hyphens right. So we're going to encrypt using 256-bit CBC AES, and this is our input file. So the first thing we'll have to do is to create that input file. And save it. And then we'll just use this command here. Okay, so that's going to take the input file and create encrypted.bin. Give it a password there, and then we'll have a look to see what encrypted.bin looks like. And we can see it's mainly binary, and mainly a binary format, although there's a word called salted at the start. And we'll find that every time that we encrypt, then we'll see the salted value even though we're outputting binary. That's not a very convenient way to be able to show our cipher, so we can use the base64 extension to be able to create our output, and we can see this time it's much easier to represent because we're using base64 format. If I now try to re-encrypt, same password, then we should find that the cipher changes. But look, it doesn't change completely because the part at the beginning is almost the same, and that's because the salt or the nonce value is contained at the start somewhere. This spells out the word salted in here, as we saw before, and then the salt value comes after that, followed by the cipher. Okay, so what we'll do next is we'll decrypt our encrypted cipher. Again, I used the password Napier, so let's get this right. And there's the decrypted value. We use the -D option to be able to decrypt using the same AES value and mode, 256-bit CBC, and we've just defined the password here, which is used to generate the key. Okay, so for the next bit, we'll use public key encryption. So with public encryption, we have two keys, a public key and a private key. We can encrypt with one and then decrypt with the other one. So let's generate our Rsa Key Pair. And in this case, we're generating 1024-bit Rsa keys. That's about the smallest Rsa key size that we normally deal with. Okay, it didn't take too long to do that. So now we can list what our key looks like. And there it's there. So we see the word begin private key at the start and end Rsa private key at the end. This is a key pair, so it contains both the public and the private key in there. Next, what we can do is we can view the Rsa Key Pair for the parameters or the attributes that the keys have. Okay, so here we are here. So what we see here, and this is both a public key and a private key, is that we have a public modulus or n value. That's twice as long as our prime numbers. So the two prime numbers P and Q are here and here. When we multiply prime 1 times prime 2, we get the modulus. So we can see here that the modulus is twice the size of the prime numbers. This is the difficulty of Rsa, in that it's very difficult to factorize this value back to the two prime numbers. If we can, then we can crack Rsa. There is then a public exponent, or E, and that's normally 65,537. Then there is a private exponent, or D, which is this value here, which is about the same length as the modulus. Our private key is D and N, and our public key is E and N. These two prime numbers are kept secret and are randomly generated. Okay, so that's the core values that we have for our public and our private key. So it's very important that we encrypt our private key just in case someone tries to access it. So we'll use DES, in this case, Symmetric key, to be able to encrypt our key. Okay, we're taking a private key and then we're encrypting it with DES to get our output. to have a look at that, then you can see this is now an encrypted private key. It tells us what the mode and the encryption method actually is, and the salt value that's actually been used for that. That then gives us our encrypted key. If we want to decrypt that, then we'll have to provide the password for it. So next what we'll do is that we'll take the key pair and we'll extract the public key, which can then be distributed to anyone who wants to use it. Okay, so we'll take our key pair, we'll output a public key in a PAM format. That's just like this base64 that we have. Okay, so we'll have a look at that. And what we should find is this is our public key. It's smaller than the private key because the E value is a smaller value, but this also contains the modulus n. So what we'll do is that we'll encrypt some data with our public key, and this is if someone wanted to send us some encrypted data, they would send it with encrypted with our public key, and then we can decrypt it with our private key. Okay, so we're going to encrypt with the input key, that's the input, and then we'll create this file.bin. There. Okay, so that's our encrypted cipher there. We could convert that into base64 if we wanted, and then what we'll do now is that we'll decrypt with our private key. So just paste that. Okay, so our input key is our private key before we used our public key. Taken our cipher or encrypted text with the public key, and then we're going to decrypt, and we'll just see if we have the right answer, and we do. So that's worked perfectly. Next we'll look at digital certificates and how we can create them. So one thing that we do is we take our key pair and we can create what's called a code signing request. This will allow us to be able to pass it to a trusted entity such as GoDaddy, and for them to sign that public key with their private key and verify our public key, our key pair. Okay, so we're going to use our private key, our key pair, and then we're going to create a code signing request. Okay, we can put in the details of our certificate, and just let me put in some details here. Okay, so that should have created a code signing request. Now what we'll do is that we'll have a look at now creating a certificate which has been signed by a private key. Okay, so this is taking our code signing request, and then the code, whoever's going to sign the certificate would then take their private key, sign the certificate with that, and create a digital certificate. Okay, so everything's fine there. So we'll just see if we've got that, and we do. So now what we'll do is we'll just browse to that. That's en route. So we'll look at the code signing request first, and there it is there. So this is a PKCS10, which is a code signing request format, and we can see the key contained, the public key that we're passing to the signer is RSA, 1024 bits, and it has a SHA-1 fingerprint for it to verify that the key sent is correct. Okay, and this is the signing algorithm, which is RSA signing. So the trusted entity will receive that code sign request, add their private key onto this to create a signed digital certificate. So let's have a look at that. Here's the certificate. We can see it has an expiry date. There's some of the details that I added for the certificate. And then we have our fingerprint for that signed certificate, the public key from before that we saw from the code signing request, and then a signature. So this is the signature of the certificate that's been signed by the private key of the trusted entity. Okay, so let's go back to where we are. And so the next thing that we'll do is that we'll actually see if we can read some hashed values. So for this, we'll just pull up another browser. Just go here, and then we'll put in these values. So first we'll try Falkirk, and we see it's 48, which is this one here. So this value is Falkirk. The next one, Edinburgh, is 03. The first one is Edinburgh, then Glasgow, and that's D5, which is this one, and then the final one must be Stirling, which is the EE. We can count the number of characters that we have, so we should find that there are 128 bits for MD5, which is 16 bytes, and each byte is represented by 2 hex characters, so there should be 32 hex characters when you count them. When it comes to SHA-1, there are 160 bits, which is 20 bytes, and 40 hex characters. For SHA-256, and we have 32 bytes, or 64 hex characters. Okay. So in the next part of the lab, what we'll use is OpenSSL to be able to discover the passwords that we've used. Okay, so the format that we're going to use is this here. Okay, so we're using APR1 in most of the cases. There's a salt value here, and this is the password. So we try that, then we can see what the hash value actually is. So what we need to do is to be able to determine which of these has the password of password Napier Inkwell or Anchor123. Okay, so we'll just try each one in turn. We'll take the salt value. And then we'll try the first one, which is password. And it's not that one, so we're looking for an M1 at the end. So we'll try Napier. And that's the right one. So the first one, the password is Napier. So we'll try the next one. And here is the salt value between the dollar signs. So it's not Napier. It's not password. Inkwell. No. And Inco 123 is the right one there. Okay, so the second password for Mike is Inco 123. So for the next one, we'll try it. Starts with a J. Ends in B. Okay, it's not that one. Let's try password. It's not that one. So looking for an S0 at the end. Or that one. It's that one. So this password is Inkwell. For the last one, we'll see that there's a 1 in there. In this case, it's not APR1, but MD5. So if we try this one, we've got to change the method. Just let me check. So it's R to N, and we're looking for 7 dot at the end. And that's it. Okay, so the password here is Napier. Okay, so the next thing we're going to do is that we're going to just download these files. And extract them. Okay, so we'll use MD5 sum to be able to find out which one has been changed. So that one hasn't been changed. That one is giving the wrong signature, the wrong hash value. This one looks okay. And the final one is fine. So the text file that's changed in this case is 2.txt. Now what we'll do is that we'll download these files, and we'll just extract them here, and we'll have a look at them. They're PostScript files, so we should be able to view them here. So we can see that one, and we can also see that one. So you can see that they are different from there. Now what we'll do is that we'll run mdsum, and for order.ps, and you can see here that they give the same Md5 hash, which means that we have a collision, and you can see that we have different content in each of the files. They will be completely different. If you've ever seen a PostScript file, you'll know it looks like a bit like that. And for that one, it's different. Okay, so in this case, we've created a hash collision. Okay, in this part of the lab, we'll take some hashes. So in this case, we have some Md5 hashes here. So just let us try these ones. And then we'll have a dictionary, just a small dictionary, just to show how it actually works. But we'll paste our hashes into here with a new line for everyone. And then we have a number of passwords that we could try. So that's Napier, password, Inco123, and Inkwell. If we want, we can run a benchmark before we try, just to see how fast our hashing will be. And for that, we use the -b. So the -b will benchmark, and in this case, we're going to benchmark Md5 hashing. So it just takes a little minute, but we'll see how fast it goes. So about 317 mega hashes per second, which is pretty fast. Okay, so we'll give this a try. So it's -m0, #1, and words. Okay, so it's managed to crack all of those. Cracked 3 of them, and it didn't crack the last one. So we'll just have a look at that one. Let's check that we've got all the words in there, and it should be Inkwell. Okay, and it's got that last one. So it doesn't show the ones it's cracked before. If you want to see them, then you do the -- show from there. Okay, so the first one is Napier, second one password, third one Inco123, and then the fourth one is Inkwell. So now what we'll do is we'll see if we can find this one. Call it words 2. Paste clipboard. And these are names of fruits. So let's see if we can get this one. So lemon, sorry, apple, orange, melon, and what else? Well, we'll take those ones and we'll see how we get on. Okay, so we'll try that one. So it's now called I've called the words to for our hashes, and then this is the fruits here. Okay, so it's managed to get 2 of them, which isn't too bad from there. But if you can download a list of fruits, then you should be able to find the other ones in there. So the ones I've managed to crack are this one and that one. So there's still another 3, but you can try with the with a bigger list of fruits from there. Okay, so for the next part, we'll take a Windows dump here, and we'll use John the Ripper to be able to crack this one. So we'll call it hash3 and paste that in there. Just let's check that we've got a new line there, that's fine. Okay, so 500 is the admin account, and then 501 is the next account after that. So we can run John with hash3. Okay, so it's found them there. So we have orange and we have apple. We can see they're in uppercase because the previous Windows passwords LM hashes were uppercase values. So let's try the next one. And it's automatically detected that we're using an LM hash here. So then we'll try this one. And we'll call it hash4. Paste. Just let's see if we're okay there. And we are. So then John hash4. Okay, so it's managed to find Dundee and Aberdeen from there. Okay, so we can do the minus show again, and you can actually see what the values actually are that it's managed to crack. Okay, so there's another one there that you can try out. Now we'll try this one, which should be animal values there. Okay, so to John, and we can see that we've got a number of them there. Do our show again. I can see snake, tiger and elephant. Okay, so in this part of the lab we'll run some Python code. We'll just download it and then extract it to our home folder. There we go. Okay, so that's working. So this is the input message. this is as hexadecimal, and then we have padding here. So this is CMS, which will pad 11 characters, so we get a 0B. If I had another character, it would pad with 0A. This is then the cipher that we have, and then we can see that we can actually decrypt. If we look at the code that we have, and so we have cipher 01. It's our code here. So we're using the hazmat library, and this is our encrypt here. And we have a mode that we apply. So in this case, the mode is ECB that we're using. This is the block size of 128 bits. This is the padding that we're using, PKCS7. Gives us that padding that we saw before. And the mode that we're using is CBC here. Okay, we're generating our key from taking a hash of a SHA-256 of the password. We don't normally do that. There are better methods of doing that, but in this case we'll just take a hash value and then we'll create our 256-bit key to encrypt the data. Okay, so the encryption key is created from creating a SHA-256 of our password. The size of the key used is actually, if we have a look, then we should see it's 256 bits in this case. For our size, and there's the, so the hash is a 256 bits value there, and we're using ECB as our mode for our encryption. So what we want to do next is to add in a couple of extra options so that we can use this with a command line. So in this case we'll add in some extra code in here. And this will allow us to pass in our arguments for the text input and also for the password. Okay, we'll just give that a little try, just see if it's still working. That's fine. So if I try hello 123, it's not working there. Hello 23. Let's see where we went wrong. So val and password are there, and then when we run val and password, process. And we just need to move that. Password. Context is equal to the value there. Okay, so we can see that we're now passing in the value of hello 123, and this part is our password. So if I want, I can put in with spaces. and it'll read it in like that. So if you watch now to see the padding change, you'll see that becomes 6, 5, 4, 3, 2, 1, and watch what happens next. So then we go on to another block from there. Okay, so that's the code that we have there. The code that we've added in just reads into arguments here for us to be able to set the plain text and also the password. Okay, so if we try a few, then hopefully, then we try a message of hello, another 1, 2, 3. Okay, and there is the cipher that we get, that we've checked there. So a message of inkwell and a key of orange gives us that. Okay, so in this way, every single time we run it, we get the same cipher because we're using ECB mode.